Okay, so welcome to our afternoon session for this BOURBAKI seminar. We will now listen to François Labourie, Université Côte d'Azur, and François will tell us about the asymptotic counting of minimal surfaces in three manifold. Those are work by Calgary, Marquez, and Neves, and maybe François will introduce his own twist on this asymptotic counting. I recall that the exposé written by François accompanying this lecture is available on the website. Maybe we'll put the link as well on the chat so that you can read François' note while you listen to him. So François, it's up to you.
Hello, good afternoon. So thank you for coming. So I will speak in my weird English. Okay. So I want to talk about asymptotic counting, what it means, and most of my talk will be a tour in some kind of mathematics, and at some point I will explain one of the results of Calgary, Marquez, and Neves, but it takes some time to build up the actual statement. So let's start with the basic example, the one which is the motivation, which is the counting of geodesics in a negatively curved manifold. So through all this lecture, H will be a Riemannian manifold with a negative curvature. So H is the metric. And most of the time I will assume the manifold is closed. And when it is not, it's usually the universal cover, which is called M2. So one of the basic facts that you learn when you learn about negatively curved manifolds is that there is a bijection, a one-to-one correspondence between a homotopy classes of maps from S1 into M. I mean, just homotopy classes of curves and closed geodesics. So this is achieved through some minimizing process. And the main statement is to say that given any curve C in M, then there exists it is freely homotopic to a unique, a closed geodesic. And moreover, the length of this geodesic is a minimizer among all the possible lengths of all curves, right? So now if you want to count those geodesics, of course you can't, because the other thing that you learn when you start learning about negatively curved manifold is that the pi1 is infinite and the set of conjugacy classes is infinite. So this means you have infinitely many geodesics, so there is no way to count them directly. So what you do is you count them asymptotically. So you try to understand, so this is the next slide. You consider the space of a, which is called gamma h of t. So h is to emphasize the fact that this depends on the ambient metric, and t is a real number. And this is just a space of closed geodesics of lengths smaller than t. And what is not very difficult to show is that this number is finite, in that the number of those geodesics, this set is a finite set. So a way now to count is to count to understand what is the asymptotics of this number gamma h of t in terms of t. And one of the basic objects that you introduce is a topological entropy. So this topological entropy measures how exponentially the number of this geodesic grows with respect to t. So here is the precise definition. So the topological entropy, so top here is for topological. And again, MH is my closed Riemannian manifold, and H is something with a negative curvature. And this is a limit when t goes to infinity of the logarithm of the number of that divided by 1 over t. So essentially it says that gamma h of t, if this is well defined, behave like e to the h t, something like that. What I'm saying is wrong, but it says something like that. So the first thing, of course, you have to check out is that this is well defined, right? So far, it's just this limit may not exist at all. Okay. So one of the celebrated results in the subject, which is due to independently to Bowen and Margulis, so in 769 for Margulis and 72 for Bowen, is that the topological entropy is well defined. So by which I mean the limits I explained before is actually a limit, okay? And the other thing that you have is you actually have an exact computation of what is the topological entropy when the metric here is hyperbolic. So I'm going to use the standard notation, the standard definition that the metric is hyperbolic if its curvature is constant or equal to -1. Okay. So if you have a hyperbolic metric, you know that you are a quotient of the hyperbolic space of dimension n. So the result for a hyperbolic metric is that this hyperbolic metric is precisely equal to the dimension of m -1. So for instance, for surfaces, it is 1. For 3 manifold, it is 2. Right. So that is a really fantastic result, but you have another quite remarkable result, which is the so-called rigidity of the entropy. So there's various versions of this rigidity of the entropy, and I guess the strongest one is the one by Besson, Courtois, and Gallo, so in 1995. It said that if you have two, if you have two Riemannian manifold, I mean, if you have you have two metric on the same closed manifold, and one of them is hyperbolic, okay? And these two have the same volume. Then the topological entropy of H is greater than the topological of entropy of H0, which I recall you is a dimension of m -1. Not only you have this is very nice inequality, but moreover, you have an equality only if H is the metric H is hyperbolic. Okay. So this is what it is called the rigidity of the entropy. You have an inequality for the entropy, and this entropy is only realized, this equality is only realized whenever the metric is actually hyperbolic. So you need to have some hypothesis like that, because the entropy, as you can check, it's something which is if you use the metric system, it's in 1/meter. Okay, so you have to have some normalization for this quantity. Okay, so now we move to another situation. So what we just did was some sort of counting of homotopy classes of a circle in your manifold. So the next step, the next logical step would be to understand what happens to surface group. So let's consider our favorite surface, which is a surface of genus G. So G is here. And it's closed, it's connected, it's oriented, and the genus is greater than 2. So in other words, your surface is a compact quotient of the hyperbolic space topologically. So now you want to count a homotopy classes of maps of SG into M. So remember that before we are counting a homotopy classes of map of the circle into M. So you have to make here a little restriction so that to make sense. So you just want to consider those incompressible surfaces. So a surface is incompressible by definition if it's pi1 inject in the pi1 of M. So it just means that if you don't want to learn about a fundamental group, it just means that if you take any loop on your surface, if this loop is contractible in M, it's actually also contractible in the surface. Okay, so typically a surface in R3 is not incompressible. So now what you want to do is something happened, and you want to consider the space of the set of those incompressible map. I mean, by which I mean homotopy classes of incompressible maps of your surface into M. Okay, so it's just a set, the set of all homotopy classes of maps from your surface of genus G into M, which injects at a level of pi 1. So it's very long to explain, but it's actually a very simple concept. Right. So let's explain some of the results here. So now assume that, so the assumption is that you have a manifold closed and the curvature is strictly negative and the, right, M is closed. So the first result is a result of Thurston, which is say that this number is finite, this set is finite. There is only finitely many classes of incompressible surface group of a given genus in the pi 1 of M. So I gave the complete proof in the notes, and it's a very nice argument and very short. It takes about half a page. And I think it's worth, it is worth knowing. But then there was a very central question in the hyperbolic 3 geometry, which is, can you prove that this number, it's finite, that's fine, but it could be 0. You could have no incompressible surface group into the pi 1 of the 3 manifold. So as most of you know, this is a achievement, I kind of thinking it was recent, but it's already 15 years ago, which is a result of a Kahn and Markovich. So now I should say that you have to impose for this one that the dimension of M is equal to 3. So it said that this number, has a very precise asymptotic, which is written here. So here's the difference with the what you do with closed geodesics. It's you don't only consider G, but you consider G log of G. Okay, and there is a 2. Whatever. And so this is a result of Kahn Markovich, and maybe the most striking fact about this result is that actually this number is non-zero, right? So I will come back to that later. I will come back to a more precise version of the existence of an incompressible surface. So somehow here we have something that mirrors what we've been doing for geodesic. We have an asymptotic of the number of surfaces under some topological assumption. Okay. But you should remark that this counting is purely topological. There is absolutely no reference to the metric H itself. So this counting does not see the metric on the manifold. And as we saw for geodesics, the entropy, the topological entropy depends on the metric because it can characterize whenever the metric is hyperbolic. Okay? That clear? Any questions so far? So
to me, it is clear.
I need to move and explain Caligari Neves Marquez result. But so this result is also an asymptotic counting of surface groups in 3 manifold, but there is some extra it depends on the metric on the manifold itself. So before that, before explaining that, I have to explain to you a few things about surface group in the isometric group of the hyperbolic free space. So from now on, I'm going to always assume I'm in dimension 3. Okay. So, so let's start with the hyperbolic free space. And for the hyperbolic free space, you have a nice model, which is a Poincaré ball model. So that's that is the ball. So in this model, H3 is the interior of the ball, and this ball has a boundary, which is a sphere. But this sphere is usually called the boundary at infinity of H3. But it's quite important to see that this sphere is actually CP1. Okay, so why is it CP1? Because the group of isometry of H3, this is like PSL2C. And what we say that the action of the isometric group on the interior extends to the boundary at infinity, and then it is like the action of PSL2C in CP1. I don't know, maybe say an action is like another one. It's not very BOURBAKI way of saying, so maybe I should say isomorphic, but let's say just like. So here, so now what about one of our favorite objects, which is the hyperbolic plane? So the hyperbolic plane in this Poincaré ball model, it's like a little disk inside, and it defines a special object in the boundary at infinity, which is a circle. But it's actually a circle in the geometry of CP1. So the complex projective space has some natural way of some natural circle. So maybe I should write that here. So if you take a real plane in C2, then you have a certain circle inside CP1. And this circle is precisely the set of those lines in CP1 which intersects P in a non-trivial way. So every real two plane defines a circle, and so you have a natural notion of what is a circle in CP1. Okay. So now this allows us to introduce a special class of surface group in the isometric group of H3. So the first thing you do is you define what are function groups. So it's just a discrete co-compact subgroup in isometric group of H2. And then using the picture I just explained before, you can actually embed the isometric group of H2 into the isometric group of H3. So this space is, so it could also be described as a set of those discrete group gamma in the isometric group of H3, which are isomorphic to the fundamental group of a surface group of genus G, and which preserves the circle. Okay. The expert have noticed that what I'm saying is totally wrong because I have to talk about torsion and everything, but let's forget about that. Okay. So you have this natural class of surface group in the isometric group of H3, which come from surface group in the isometric group of H2. So then what you do is you can extend this notion to define a quasi-function group. So what is a quasi-function group? It's just, it starts with the same definition as before. It's a discrete group in the isometric group of H3, which is isomorphic to the fundamental group of a surface group, and thus preserves an embedded loop in the boundary at infinity. So this loop is not necessarily a circle. It might be something, it is usually something very wild, but it's still an embedded loop. Right? I don't want to talk about circle because I want to think of circle as this very rigid object in CP1. right? So let's do a little drawing. So this is an object here, which is this loop, and a quasi-function group is something that preserves a loop like that, okay? Which is not necessarily a circle. So it turns out that this loop so I said before that this loop is actually denoted at the boundary as a boundary at infinity of gamma itself, right? So it turned out this loop has some nice property. So let's give a general definition because we're going to need that in a few minutes, which is that to say that a loop in the boundary at infinity of H3 is a K quasi-circle if you can have a parametrization of it by the real projective space, and this parametrization satisfies some nice property. So this property is written here. It is to say that if you take the image of 4 points, you can compare the cross ratio of these 4 points in CP1 and the cross ratio of these 4 points in RP1. And it is just related by this constant K. Okay. So even if these objects are nice, it turned out that the one I just drew is certainly not a quasi-circle for K is equal to, well, let's forget that. Sorry. Turn out, forget what I said. Okay, so that's a definition of what is a quasi-circle. And so here's a nice property of the boundary at infinity of a quasi-function group. So the boundary of a quasi-function group is actually a quasi-circle, K quasi-circle for some K. And in that context, you say that gamma is K quasi-function. So it turned out that there's lots of quasi-function groups in the isometric group of the hyperbolic free space. Okay? So I've described a class of group in the isometric group of the hyperbolic free space, which are isomorphic to surface group and which preserves a boundary at infinity. And this boundary at infinity has some nice property, which is this K to be a K quasi-circle. So let's explain now the Kahn-Markovich surface subgroup theorem which is due to 2006. So it says better than there exists a surface group. It says that you can find the surface group which is as circular in some way as you want. So it says the following. It says that if you take a closed hyperbolic 3 manifold, and if you take any positive epsilon, then you can find a 1 plus epsilon quasi-function group in the fundamental group of N. I should say here something which I forgot to say before, that if you have a quasi-function group, then it's actually a function group. It actually preserves a hyperbolic plane. So for many reasons, there are very little chance to find a totally geodesic closed surface in your 3 manifold. This happens very rarely. And actually, there is a beautiful recent result that says that if you have infinitely many such closed totally geodesic surface in your hyperbolic 3 manifold, then your 3 manifold is what is called arithmetic. That's a recent result of Bader, Fisher, Miller, and Stover. Yes. Right. And so here is the Kahn-Markovich surface group theorem. And this is actually used, this is going to be used in the statement of the Caligari-Neves, Marquez-Neves asymptotic counting. And the proof of it is actually used in some way inside the proof at some point. And I hope that we'll have time to see why. Okay. Right, so let's move now to Caligari Marquez Neves asymptotic counting. So here are your situation. You start with a closed three manifold. I'm sorry. So here this is a closed, M is a closed three manifold. And it's equipped with a metric of curvature less than -1. And I will keep sticking to my notation. Then H0, when I have H0, it's a hyperbolic metric. Okay. So now let's start with a homotopy class of map from SG into M. And maybe I should add that this is again an incompressible map. So then I define the minimal area of P of pi, which is the infimum of all the possible area of the map F from SG to M. So for instance, if instead of taking a surface, I would have taken a circle, I would just end up with the length of the closed geodesic in the homotopy class. Right? So this notion depends on the metric, right? Because this area is measured using the metric on M. Okay, and the other thing that you do is you compute some invariant of pi, and you say epsilon of pi is less than epsilon if pi is a 1 plus epsilon quasi-function group. Right, so this homotopy class of a surface into M is the same thing as a conjugacy class of mapping of the pi1 of the surface into the pi1 of M. So it does make sense to say that the homotopy class is quasi-function or not. Okay. So you must notice there's something a little weird going on, which is here this quantity depends on H, and here this quantity depends on H naught. But we are lucky to have amazing theorems. So one of them is Mostau rigidity theorem that tells you that you can only have one hyperbolic metric on a given manifold, a given closed manifold. And the other one is, of course, Perelman uniformization that tells us that if this metric has strictly negative curvature, then it also admits one hyperbolic metric. Right. But still, you notice that this quantity depends on H and this quantity depends on H naught. So now we can start counting. So we consider the set, which depends on H, of those homotopy class whose mean area is less than A, and that the boundary of the surface group corresponding to pi is 1 plus epsilon quasi-function. Right? So you don't count all surface group, you only count those surface group that are 1 plus epsilon quasi-function in some way. Now, the next thing you do is you play the same game as computing the asymptotic. And now that's the same counting function that we used. Oh, sorry, I missed the log. Right? So this is the same counting function that appears in the counting function for respect to the genus. So that is 4 pi because, well, 4 pi exists. And then you consider this quantity. And then finally, the second step you do is you take the limit of that when epsilon goes to 0. It's quite easy to see that this is decreasing in epsilon, and this actually is the limit. So the objects that you consider now depend only on the metric H. So it measures the growth rate of a surface group whose area goes to infinity, and then after whose epsilon of pi goes to 0, meaning that this surface group at infinity becomes more and more circular. So again, you notice that it has used both H and secretly the uniformization theorem to make sense of this epsilon here. Okay. So now here's the result of Calegari, Marquez Neves. And so again, here is the hypothesis. So you have a closed three manifold. It has curvature less than -1, not greater than -1. The dimension is 3. And the metric is, and then you use your stick to this notation that H0 is hyperbolic. Okay. So here's the result. It say that, so first it gives you a computation of what happens when the metric is hyperbolic. So this computation that whenever the hyperbolic metric is hyperbolic, then this quantity only depends on, it depends on nothing, and it's equal to 2. Okay. So it does not depend on the manifold, or it's not a topological number, it's just 2, right? Like the entropy for closed geodesic. The second part is that you actually have a superior bound for the entropy of H, for any H. So it's less than the square of the topological, it's less than twice the square of the topological entropy of the metric. So at least you see that it's coherent because this is in 1/square meter, and this is 1/square meter, and this is in 1/meter. So it's a correct unit. And what is the most interesting part in the result is the fact that you have this inequality, and you have equality. So this equality here is that inequality that this quantity is greater than 2, and the equality is only if this H is hyperbolic. Okay, so these are a series of results that mirrors exactly what happens for geodesics. So remember that for geodesics we have the computation of the topological entropy, which is given by Bourbaki and Margulis. And well, we don't have that, of course. And then we have this result. So actually, this version, because we have the curvature is less than -1, is more an earlier result than what was done by Besson-Cotre-Gallo. It's a result of Consu on Hammenstedt. And but my notes are more precise about all that. Okay, so I should have said from the very beginning, so I'm going to say it. So I'm going to give you a hint of the proof. And I'm going to explain to you what happened when the metric H is close to be hyperbolic. Right, so this is going to be a somewhat complete proof when H is close to hyperbolic. And but it doesn't work when we go far from hyperbolic. So they have to use some extra argument.
So I have a question.
Yes.
I'm wondering, why do they have the epsilon pi? I mean, because it'd be too larger without the epsilon pi, the set of matrix or surfaces you consider.
So
I mean, why? Yeah, I mean, in the definition of I don't know. I guess it's
right. Why do you have this epsilon pi?
Why do we have the epsilon pi?
Because I don't know. Maybe because that's well, that's a good question. But it turns out that there is no nice result when epsilon when you don't have the epsilon pi. Of course, you have lots of inequalities, because if you delete the epsilon, then you have lots of inequalities, right? But maybe you will see in the proof why epsilon pi is useful, and yes, why. I hope that you see in the proof why you like your epsilon pi to be small.
Okay, thanks.
So that's going to be explained hopefully in a few minutes. Okay. So I should first say that most of the results here, they are actually consequences of the counting in the genus. Most of the inequalities, except the most interesting result in my opinion, which is the equality case, right? So why do you have that? So remember that we have this asymptotic in the genus, which is given by Kahn and Markovich. And how do you relate an asymptotic in the genus to an asymptotic in the area? So of course, if you have an inequality of the form, let's say A greater than Kg minus C, or Kg plus C, or A greater than Kg minus C. So if you have an inequality like that, then you obtain an inequality for the asymptotic counting. And if you have an inequality like that, you obtain an inequality for the other counting. And the inequality in the other way for the counting. So let's give one example. So one example is this. Is that you have a nice, very nice result, which is, so let's say that, let's go a little bit ahead of ourselves and say that your surface can be actually represented by a minimal surface. And because you have a minimal surface, it follows that the area of this minimal surface, I mean, the curvature of this minimal surface is less than -1, is no greater than -1, because of all your hypotheses you have on M. So this implies that the area itself is less than 4 pi G minus 1, is by Gauss-Bonnet. And from this inequality, on the fact that you have asymptotic counting with respect to the genus, on some let's say set theory, you obtain that you obtain this inequality, right? So most of the inequalities that you get are obtained by some very nice observation about the relation between the minimal area and the genus. Okay. So let's try to focus on what I like the most, which is the equality case. Right. So maybe it's time to go back to geodesics. So the point about geodesics is the way I presented the result. There was some kind of a cheat, because I always talked about closed geodesics. But it turned out that all the proof uses the fact that these closed geodesics, they are part of a larger collective. They are part of a whole family, which is the space of all geodesics. So let's define the space of geodesics in general. So you consider the space of the universal cover of M, which I denote by M Twitter. And you consider the space of geodesic, which is a space of isometries. I mean, really isometry, preserving the distance between R and M. Okay. So that's the space of all geodesics. And I put some topology on it. And the topology I add is a topology of, let's say, smooth convergence on compact set. Okay, so let's see what we have on this space, what sort of structure that we have on this space. So the first thing that you have is you have an action by R. So the action by R is just the action by precomposition on R. So R itself is a group of isometries of R. So it acts by precomposition on the right. on the space of isometries, on this geodesic space. So this is something that most of you know under the terminology geodesic flow. The other thing is that you have a natural projection from this space to M twiddle itself. So to a map F, you just associate its evaluation at 0. So you also all know that it's just a projection. If you identify this space with the unit tangent model of the manifold, this is just a vibration from M. So I'm just going to emphasize here some much easier property, which is, it's not a vibration, but at least it's proper. It's a map which is proper. So if a sequence of map of isometries from R to M, if f of 0 converges, fn of 0 converges, then the fn subconverges to something. And the other, finally, property that this is a natural object in a sense that if you consider the isometry on M twiddle, now they act on that by post-composition, meaning on the left. Okay, so here are 3 properties of that. You have this R action, you have this evaluation map, which is proper, and this group of isometry acts on that. Okay. So here and let's introduce another definition. Oh, okay. So maybe let's first talk about that. So when you take a closed manifold, so it's better to define this space now as the quotient of the space of geodesic of the universal cover by the fundamental group. Okay. So in the context when the metric is hyperbolic, or let's say, okay. So this space is actually, it's homogeneous under the isometric group, and the K here is a compact subgroup. And the action of R on this space becomes some algebraic action. So here, the diagonal group is only in the case when, sorry, the dimension is equal to 2. Right, so that's a geodesic flow. You have all heard about it. And I'm just re-explaining what you all know. So now, how do you see the closed geodesic? How do you see this space? So this space has a nice structure because of the R action. It has some local charts. So here I'm in G of M. So where M is a closed manifold. So this has some local charts. And these charts are locally product. And these little lines with arrows that correspond to the action of the R action, so orbits of the R action. And of course, now you see what are the closed geodesics. So the closed geodesics are a closed orbit of the R action. So this means that if you start with this object and you continue it in some other patch, then eventually it will close up. Okay. So you see the closed geodesics, now they are part of a larger collective. They are the closed orbit of some R action on this space. Right. So I need to explain some extra thing, which is actually what is very useful to consider on this space is not only the closed geodesics, but also the invariant measures on this space. So I want to explain at least one way to construct a R invariant measure on this space of geodesics. So again, M here is closed. So if you have a closed leaf of length L, this corresponds to a nice R invariant, and maybe I should add probability measures. So I guess the point that now everybody knows that. So those who don't know, I'm going to give a formula, and I'm not sure this is going to help them a lot. So here's the fact that how do you define this probability measure D of gamma? So you define it by what is its value under when you integrate a continuous function. And the integral of f with respect to delta gamma, this is just the integral of f on the closed leaf itself. So if you see gamma as the map from R into M, you see gamma here as a map from R into GM itself. And so maybe I should have explained that you have gamma. So this is a map of R into M. But you also have a map, let's say, called gamma Twitter, which was associated map from R into GH of M. So let's make that correct. So so gamma tilde of T is just gamma of T of the, I'm sorry, it's just the map which associate to S gamma of T plus S. Okay, so if you move the point along the geodesics, it gives you a curve in the space of geodesics. I'm sorry for the complication. So anyway, the point is that this you have a natural measures associated to any closed leaves. Okay. So a beautiful result, which is also due to Bowen-Margulis at the same time, and which is actually intimately related to the result I explained before, is to say that closed geodesics become equidistributed. So it means that if you take the sequence of this, this was not supposed to happen this way, sorry. So if you take the sum of all these probability measures, which are located at gamma, when gamma is a curve, is a geodesic of length t, and if you take 1 over the number of that to turn that into a probability measure, this converges to what is called the Bowen-Margulis measure. And when M is hyperbolic, when the metric is hyperbolic, the Bowen-Margulis measure is actually the Lebesgue measure in the Lebesgue class, which means that it's a unique invariant measure on G of M, which is on the space of geodesic, which is invariant by the isometric group. So it's quite important that this geodesic is becoming equidistributed. So now I want to play the same game for minimal surfaces. Oh, I need some last stuff, and maybe I need to hurry a little bit. And there is yet another interpretation of what are a invariant finite measure on G of M. It's related to what is called a Bonaon current. So what is a Bonaon current? So it's locally finite. Now, instead of being invariant by R, you consider it invariant by pi one of them. And now it's not on G of M, it's on the boundary at infinity, on the space of distinct point in the boundary at infinity. So again, there is it's better explained, hopefully, in my note. And there is a formula which is here, which I cannot access to. Yes, it is. This formula is not going to comment on it and move to what you do. So now I'm going to talk about minimal surfaces. So there is a huge literature on minimal surfaces. I'm going only to state one result, which is going to be specifically useful here. And in my notes, there are more results. And important like Shenyao's or Anderson's, and result also very nice result by Sepi. And so let's explain these results. This is a result which is due to Karen Uhlenbeck in '83. So it tells you the following. So now imagine that you have so instead of So before, these pictures was to say that if you have a geodesic, it actually has 2 points at infinity. And the geodesic is totally determined by these 2 points at infinity. So now you have the same idea for a minimal surface. So you want to have some data at infinity, which characterize the minimal surface in some unique way. So minimal surface just means that it is locally area minimizing. So it's like geodesics, but you replace the length by the area. So, so here's the result of Uhlenbeck. Tells you that there is some small epsilon zero, some positive constant, not zero, so that if you take now any quasi-circle and in this boundary at infinity, then you can find a unique minimal surface S, which is bounded at infinity by this set lambda. So this result is not true, and there is some counterexample, when epsilon zero is large. But it is true when epsilon zero is close to zero. So this result is a priori just for a hyperbolic metric, but it turned out that this extends also for a metric which is close to being hyperbolic. Okay, this is just because the fact that you have a unique minimal surface sort of say you that you have some compactness theorem behind, and because if you have some compactness theorem, it's going to be true not only for the hyperbolic metric, but for a nearby one. So here is a really waving my arms proof of this fact. Okay. So using this Uhlenbeck result, so in the same way that we said that a geodesic is defined by 2 points at infinity, we can do that for minimal surface. So let's consider the analog of the geodesic flow. So we just consider space. So M twiddle is the universal cover. H is a metric which is close to be hyperbolic again. And epsilon is some number which is less than the epsilon zero, which appears in Uhlenbeck's result. So the space is just as before. Instead of being the space of isometries from R into M, the space of conformal map. So replace isometry by conformal map from the hyperbolic plane into M twiddle, into the universal cover, and with the extra assumption that this boundary at infinity is a 1 plus epsilon quasi-circle. So to go from R to H2 is not a big leap of faith. You have to remember that R is the hyperbolic space of dimension 1. Okay. So let's see what you have on this space. So the first thing that you have is that you have an action of PSL2R, because PSL2R is a group of isometry on H2, it's a group of conformal invariants on H2, so it acts on this space on the right by precomposition. You also have an evaluation map, so to a map phi, you can consider phi of I. So I should have said that made H2 is the upper half plane. So I is a very specific point in the upper half plane. And this map is proper. So this is not a trivial result. It uses the fact that, for instance, in that context, you can prove they are a priori bound for the second fundamental form of the solution of Uhlenbeck result. So CEPI has some very nice explicit result about that. And then, so that is, so actually this is not very specific to H being close to hyperbolic. So here is something which is uses the fact that your metric is close to hyperbolic. So you say that this map, which associate to this to such a conformal minimal map, its boundary at infinity, this map is continuous. Right? So say that if you have a sequence of minimal mapping, which are solution of this Uhlenbeck results, and you have a sequence of these maps, then the sequence of boundaries converge to the sequence of boundaries. So that's the point where I deeply use the fact that H is being close to hyperbolic. So now it's not very difficult to show, exactly using an analog of this Bonahan current, that you have a nice homomorphism between the space of SL2R invariant measure on this space when the metric is close to be hyperbolic, and with the metric which is hyperbolic. And this is done by using an analogous of this current, which is going to be a locally finite measure on the space of Krasik circle. Okay, so you have a bidirection between measures here and measure here. Okay, so now we use a Kahn-Markovitch proof itself. So you have to go in the proof, and that's not so easy, to be fair. And what you show is that that in that context, there exists a sequence of measures which are, each of these measures is actually supported on finitely many closed leaves. And it's for, so when m goes to infinity, the epsilon here, which is 1 over m, goes to 0. And the limit of this measure.
François, this is under the assumption that E of h is equal to 2. This is.
No assumption here.
No.
This is totally general. So here's the point that this limit has full support. So for those experts in the room, you see that Ratner's theorem is also lurking around. And if you have this limiting of such measure, you're going to end up with a SL2R invariant measure on this space. And you know that this space corresponds to, I mean, this space does not have so many invariant measures. Okay, SL2R invariant measure. So you would have to be very unlucky to end up with one of these bad measures. But still, you have to prove it. And this, you have to go for that. You have to go in the proof of Kahn-Markovitch itself. So you have a sequence of measures which become equidistributed. So now here I use the fact that I want to prove my rigidity result. And I want to use the fact that this E of h is equal to 2. I'm not sure that the author gave a name for E. So now here's the result. So anytime you take a sequence of measures which is supported on finitely many leaves, and for any such sequence of measures on this 1 over m, then the limit has support on totally geodesic hyperplanes on M. So this is again an application of the fact that the counting genus and the fact that you have some idea about counting genus and you have some relation between genus and area. And the fact is that because you have this assumption delta of M is equal to 2, then essentially well, I can't give the proof, I'm sorry. So the proof is fully written in the notes. It's not terribly difficult. It's very smart, but this part is not very hard to understand. It's just half a page or something. So now you are finished, because what you prove is that any circle in the boundary at infinity. So any circle in the boundary at an infinity is in the support of this measure, right? But also, because such a measure is supported on totally geodesic hyperplanes in M, I should say really totally geodesic hyperplanes in M, meaning that you have totally geodesic planes in M. M has variable curvature, but the planes are hyperbolic. And remember, the curvature of M is less than -1. So it means that any circle in M bounds a totally geodesic hyperplane for M. And then there is a next step. Again, the proof is given in the note, which follows, of course, the result of Calegari-Marquez-Neves, that in that context, it's implied that the metric is hyperbolic. If you have too many, in other words, it's very rare to have many totally geodesic planes, many totally geodesic surface. And if this happens, your metric has to be hyperbolic. Okay. So you go from the fact that you have any circle in the boundary at infinity to the fact that you have any tangent plane in your three manifold. There is a total geodesic plane that passes through it, and that's very strong. Okay, so I guess it's over at 3 p.m. exactly.
Bravo, thank you. So thank you, François, for this talk, and please ask questions. So I have a small question on this energy-like functional on the space of Riemannian metric on M. Does it act as some, I mean,
condition also.
That is some, I mean, some kind of property of maybe, I don't know, convexity or continuity, even continuity, is it continuous with the metric?
It's not clear to me, but maybe so the well, it's not at all clear to me that this should have even continuity property, but maybe I have no idea whether this should have continuity property. I'm sorry, I don't have any idea whether this has a continuity property or not. No.
And there
I just wanted to say that maybe so the result is stated for three manifolds. So we are used as three manifold in several places. For instance, we use the Kahn-Markovitch result, but Kahn-Markovitch result has been extended in at least odd dimensions by Ursula Menstedt. And so the equidistribution, for instance, theorem should work the same way. But here's the point that I'm not really sure that the analog of Uhlenbeck result is true in that context. Well, I would be extremely surprised that it's not true, but you know, surprises happen. So I think there's a whole lot to do in extending this result to higher dimension and to other contexts. Yes, so I guess
more questions or comments? So I also believe that entropy, I mean, really for counting geodesic as, I mean, also relation with symbolic dynamics and can be interpreted there as, I don't know, some minimizer or something else related with
right. So the question is whether, for instance, if you go, so there is a so if you consider this space of this space, right? Mm-hmm. The foliated space. You could always ask whether a foliated space has some kind of coding, meaning that you can represent it as a two complex. So to code the space of geodesic is to find a graph such that any geodesic is represented, almost any geodesic is represented by a geodesic in the graph. So here you could actually ask the same question, whether you could find some kind of two complex, finite two complex, such that each leaf of your object could be represented as some sort of leaf object in your two complex.
Mm-hmm.
Well, this could be done, for instance, in some other situation, for the space of K surfaces of constant curvature. You have some sort of coding there, but the point is then go from this kind of coding to have a theory as good as the thermodynamical formalism for geodesics. I don't know. I don't know. Okay.
Yes. Maybe there are more questions.
No questions?
I have still another question. So is there a good way to feel that the correct normalization bound was G log G?
Yeah. Oh, yes. There is one way to do. One way is to remark. So, so maybe we should go back to Kahn-Markovitch result, right? Because it started there. This result. Right. So the way I stated it is I'm just counting. I'm really counting surfaces group. But for instance, a surface and its cover, they are both counted. Okay. So actually, Kahn-Markovitch result is also not only for counting surface group, but it's counting a commensurability classes. Okay, mm-hmm. which is sort of stronger, right? So let's make a little remark here. So in Kahn-Markovitch result, they count commensurability classes.
Does this mean up to cover?
Yes, not only yes. They can't come. They say that two surfaces are the same if there is a common covering.
Mm-hmm.
And but if you just want to count surface group, you kind of see that this SGM is greater than some constant C1G to the power 2G log of G. I'm sorry. Is that the correct? Yes, that's the correct thing. And so because you just see that there is this so-called so Müller-Puszta formula. Which say that the number of covers of genus G of a given surface, this in the end it grows up like some constant times G to the 2 log of G, G log of G. So as soon as you have one surface group, then you have plenty of you have a lot of other surface group, and this number grows at least like that. So I'm just trying to explain why it grows at least like that when you count just surface group. So of course it doesn't apply, this very simple argument doesn't apply for commensurability. Yeah. And what did I wanted to say? Yeah, so that's at least one explanation why you have to have something like that for accounting surface. But I guess I have no intuition, and I don't know if Vlad has a better idea, or I don't know.
Well, actually, let me ask you. Since well, one question that is, how does the random surface of genus G look like, incompressible surface? And even we don't know whether it is a quasi-Fuchsian surface or a fiber, which are these other type of incompressible surfaces living inside of tree manifolds. So we don't know how many of them there are, but we don't even know topologically how they sit inside of the tree manifold. I wanted to mention that as kind of explaining that we know actually quite a little.
Yeah, so maybe let's go back to this question of Saburo, which is, so here we are just counting surfaces which are close to be totally geodesic. But in some way, maybe the other which are very interesting are the one which are certainly not quasi-function, which are the one which are the fibers in this free manifold fibers of surface.
Yeah, so I actually don't know of which one, if you fix a genus, are there more fibers or quasi-Fuchsian ones? Yeah, I don't know.
Nice question.
Yeah, that's all I got.
Okay, so I think we can thank François again for this nice lecture and also the notes that are available. And our next session will be as well online on June 26th. And we can thank François again for his lecture. Thank you very much. Merci, François.
And well, I can stick around if you want to ask me questions for a few minutes. Okay.